Okay, so last but certainly not least is some interesting research on how to shift our metrics from those used historically to operation science-based metrics that help projects effectively use the 5 levers. So our speaker today is Guillermo Prado Lohan. Hopefully I got that right or close.
Yes, you did. Yeah.
Who has worked with public and private organizations in South America and North America in implementing of building information modeling. He's part of the technical committee that assists the Peruvian public sector with the development of the national BIM policy. His current areas of interest included BIM, lean production, and the application of operation science in project delivery. He's currently enrolled in the Engineering and Project Management Master of Science program at the University of California in Berkeley. Guillermo, welcome, and please share your presentation with the audience. I turn it over to you.
Thank you so much, Gary. Can you confirm that you can hear me properly? Thank you so much again for allowing me to present what Professor Tomalin and I were doing about this research project. I'm Guillermo Prado, as Gary introduced me. And in this case, we will elaborate a little bit more on our symposium presentation last week about how to use operation science to design production systems in building construction. In this case, we will make some comments about what is the literature review. We are going to establish some literature review about production system design, operation science, and how these two concepts will interact to each other. We are going to establish what were the research questions of this research project. We will explain what methodologies we use in order to develop this research project. And then we will focus on the case study in building construction. We will describe all this production system process, how we designed it, how we use operation science to design this production system. Then we're going to discuss what were the assumptions that we use in order to develop this application of operation science for production system, for designing production systems. And then we're going to have some relevant conclusions and further research. And finally, the acknowledgements of all the people that were involved in this research project. The objective of this presentation is to demonstrate the applicability of conducting an operation science analysis. Basically, all these topics that we were hearing throughout today's technical conference are going to be tried to be explained for the intention of designing production systems using a case study, in this case, building a healthcare building in Northern California. Hopefully, we will have some questions at the end of the presentation, and we can have some discussion based on those questions as well. We will start with the literature review, in this case, production system design. This is a concept that was what is well documented and has been applied since the manufacturing industries. They've been developing this, as most of the people in this conference were explaining and were presenting. Production system design is about managing the resources to meet the client or the customer's demands. This is very important, as we were discussing about how, as throughout today's conference, we were saying how we have to match the current demand with the current capacity and how we can interact with that and how that can help us to plan our work towards actually meeting those demands. The expected outcome of production system design can be developed whether creating a new system at the beginning of this activity, or it can be a description of the current process and how to optimize it. So we acknowledge that production system design can be developed at any stages of a current production system while a current production system is functioning. Then when we turn these concepts and try to apply to the construction industry, we obviously have some differences that we have to acknowledge. Production system design itself has been implemented in the construction industry for the last 30 years. Toscala actually stated there is the need for a new philosophy of production in construction. Most of us have read this paper from SciFi in 92. Well, he established the need for this new philosophy. Then Baller, one of the presenters of today's conference, developed with other authors a guideline for developing production system design in construction, determining and establishing the concept of project-based production system. Finally, we see a lot of interaction between production system design and the current lean construction tools and methods that we can find in most of construction companies in the United States. About operation science. Operation science is highly related with the concept of operations management and operations research. I have to mention that the intention of this paper, on this research, is not to compare discrete concepts with the intention of making similarities or differences between them, is to actually acknowledge that these three are related. Operations management, from one side, is related with managing the processes and operations that will produce services and goods at the end of the pipeline. Several authors mentioned how operation science can be applied differently and have different perspectives of how to apply it within these different contexts. Other authors suggest that it will be beneficial to have an empirical theory for operations management. On the other hand, operations research is a systematic approach, or is based on a systematic approach that will formulate and therefore provide solutions using mathematics and analytical tools. Several other authors have been trying to use operations research in the construction industry, explaining that it will be beneficial to have operations research applying to construction because it will actually seek for causes of the problem rather than from the effects of what happened in construction. And as I pointed out at the beginning of this slide, there are different concepts. We don't try to explore the details of these differences, but at the end, these two concepts, operation science, are the ones that we want to acknowledge that exist and are related to each other. We've been hearing several concepts of operation science today, but the one that we use in this research is the following. Operation science is the study of the transformation of resources to distribute and create goods and services. It focuses as well on the interaction between demand and supply and variability, and acknowledge the interaction between them and how variability might impact these two concepts. And when we are talking about variability, we also include what were explained earlier this morning about buffer and how we can have several buffers and how it can be related with actually providing what is required by the client. Then, having these two major components of literature review, which are the basis for developing this research project, these are the research questions we will try to answer. How can an operation science analysis be beneficial for production system design on a construction project, and what are the assumptions that we have to make in order to conduct this type of analysis? Here is perform instead of inform. My apologies for that. Well, the research methodology that we use was based on the 3 equations and 4 graphs that are stated in factory physics. In this case, we are only going to use 2 equations and 2 graphs in order to describe how to design a production system for construction projects. In this case, the variability, utilization, and time equation is the first equation that we are going to use, which describes how the Q time is related with the different parameters in a single Q system. In this case, we are finding one of the main operation science metrics that we will use in this research, which is utilization or capacity utilization. And we are also going to focus on the Little's law equation. My apologies for this mistake, which relates the working process, cycle time, and throughput parametrics. Then we're gonna use these two graphs. In this case, it's a production flow graph, which was already explained by several presentations earlier today, how throughput, working process, and cycle time are related. Many of these lines are actually based on the Regal's law equation represented in the previous slide, and the cycle time versus utilization graph, which describes actually how the average cycle time and the utilization are related, and how variability might impact the relationship between these two parameters. Now going into the case study, here we have the specific steps that we developed during this case study. Most of this part of the presentation was already shared during the symposium last year, but it's very important to acknowledge this third step that makes several assumptions about how we are going to make this operation science analysis within designing a production system. We are going to explain how we selected a production system, what are the beginning at the end of the production system, how we mapped, analyze, and model the production system. Then we're going to explain these assumptions, which are very important to acknowledge. And in this particular step, we are going to also mention how we can actually provide assumptions that are realistic to what is happening in the current construction process. And finally, we're going to provide some results in terms of the production of the operation science metrics that we presented at the beginning. First of all, the production system. In this case, we selected a cladding site assembly production system, which is basically the facade of this healthcare building in Northern California. We are going to model this production system since we received the components, the EIFS panels, the windows, and the caulking components, how we are going to assemble these components in the facade and in the elevation of the building. Then how we're going to assemble these windows within these openings of the EIFS panels. And finally, how we're going to caulk all these components, the surroundings of these elements of the facade. This is the production process map that we developed using SPS Production Optimizer and PPI Process Mapper. We have three major stages in this production system. First of all is the EIFS panels installation and inspection. Then we're going to go through the windows installation and inspection, and then the development and inspection of the caulking among these components. We have to mention that the actual demand that we were working with was the installation of 60 EIFS panels per day. These were engineered to order components, meaning that each of these components were designed somehow and engineered somehow that each of them have a particular position within the elevation of the building. As I mentioned in the selection of the production system, we are only going to focus on what's happening in the production side, in the construction side, meaning that we are going to consider the arrival of each of these components on the construction side, but that's our starting point. So within these constraints of the production system, we are going to use the analytics of Production Optimizer to develop this operation science analysis. In order to collect data, we had to translate a lot of the conventional project management data, such as the schedule of the project, how many people were involved in each construction crew, how many pieces of equipment they were using, and translate that data into production parameters, such as transfer batch, process batch, and demand. That was the case with the items. These items were the ones where these components that were flowing throughout this production map. As you can see here, in each of these stocks, we are going to see a transformation between these two components, these two items that were going through the same process, and then they are creating a new item. These squares represent this transformation process. So these are the items with the respective parameters and what's the demand I have to also mention that this demand of 16 EFS panels per day were the ones that were allowing us to do an equivalent of the demand of the other items that were selected throughout the production system. Similarly, we collected data about the process rate and the process time of each of the construction crew or the resources involved in the actual operation and how they were developed, each of the activities shared in this production system. So again, translating this information of project management tools such as the schedule or this Gantt chart into actual production parameters was critical in terms of, depending on the accuracy of this translation, we will be able to have either a good result or a bad result. And good result meaning that it actually reflects what is happening in the real project. And in order to develop these translations, we focus on the 5 levers of production project management based on the operation science foundation to actually take into consideration not only these numbers from these parameters, but actually collect this variability and make some assumptions about this variability. And this is actually the next topic. What are the assumptions that we had to make in order to conduct this operation science analysis? And I also want to mention that we use the analytical model component of the production optimizer in order to have these optimal results for the operation science metrics. One big assumption was to name a parameter called the square coefficient of variability, which basically assumed that by making the assumption that the process rate and the process time are normally distributed parameters, then we can say that the square of the coefficient of variation is a relatively accurate metric of the variability of those parameters, meaning that each of these parameters that I'm showing in these 2 tables have a normal distribution, and therefore the square of the coefficient of variation can be used as a measurement of the variability of those parameters. We also assumed that there was no warm-up phase in this scoring process, and that was assumed because the project team, in this case, developed a lot of coordination processes that allow them to avoid having this warm-up phase. Therefore, we can assume that that happened in this case study. Then the production optimizer, which is the software that we use, accounted for way too much time in the analytical model that we will developing there, but we didn't consider any matching problem. That's a big assumption that we made for this analytical model, and we didn't consider rework within this case study. And finally, the current activities of our production system were developed serially. There was no preemption of activities. So this is actually based on the information that we collected from the project team as well. So considering these 5 assumptions, the data that we collected and the production map, we have these results with the current demand with 16 EFS panels per day to be installed. We can see some of the similar graphs that were shown in the previous presentations today. And we see that we have our current demand, which is lower than the best throughput, considering these parameters. And in this case, we are seeing the little slow equation graphs, the production model graph, based on the EFS panels installation, considering these 16 panels that are supposed to be installed per day. In the graph on the right, we are also seeing what are the capacity utilization in terms of percentage of each of the resources that we're developing these activities. In this case, we can see that for EFS panels installation, we have a very relatively accurate measurement in terms of the capacity utilization. In this case, was around 82%. And based on the previous presentations, this is below 85%, which allow us to have a relatively stable measurements and will allow us to don't have cycle times to go too high. We can also see that the most critical resource in terms of capacity utilization is the Windows installation. In this case, is a little bit more than 82% as well. Based on these numbers, we can see that our cycle times are relatively okay in terms of the expected outcome of this production system, meaning that the actual demand was actually actually met. The current production system is actually meeting the demand intended of 16 panels per day. In this table, actually, we can see all the operation science metric, the ones that we established at the beginning, and how those are related with the production management metric. This is very important to acknowledge as well, because these operation science metrics can allow us to actually have an idea of the production management metrics, the typical ones such as duration and cost of these activities. And we compare them with the real duration of each of these activities, we actually see that the model provides us some reasonable results and are very accurate with what already happened in the real project. Some discussion that we can make about these results is that these four metrics, the equations and graphs, are allowing us to understand the behavior of the production system using operation science. This is very impactful because we can make some contrast between what we can accomplish in the production system and how it might impact in the project management role, such as the duration of the activities and the cost of these activities. Then these 5 assumptions that we made were taking into account the peculiarities of a construction production system, such as the lack of awareness of operation science metrics in most of the construction projects. Then there is a lack of understanding of the impact of variability and the excessive amount of work in process activities within most of the construction projects. And there is a lack of ability to stabilize work plans. And the last peculiarity of the construction industry of construction projects is that the steady state assumption may not always be applicable for all these construction processes. Finally, we have to acknowledge that the operation science analysis presented was developed based on stochastic models, and the results are not always so obvious to most of us. But when we make the reasonable assumptions actually we work with a project team that will allow us to make those realistic assumptions, we can actually have results that are actually showing what already happened, as we are then demonstrated here in this chart. These results are pretty similar to each other. Therefore, our model was providing good results to make decisions. And as I mentioned at the beginning, a significant challenge of applying or implementing operation science in construction is how to collect data. And production data is not so obvious in construction sites or in general in any project. So we have to establish ways to translate these project management documents or tools and how to translate this data into production parameters. As a conclusion of the whole research project is that we actually answered those initial questions. Operation science is applicable by making the right assumptions and acknowledging the existence of a project-based production system, meaning that we will have a temporary production system and we have to study it in a very specific way and using the context as the baseline. The software that we use provided by SPS, the production optimizer, actually provided the means to use this operation science analysis, and by using the analytical model, we were able to conduct this case study, which provided these results, and therefore made possible the applicability of operation science to design production systems within a construction project. These production parameters can be translated by using the right assumptions and collecting the right amount of data from the project team and from the project plans and project tools. Regarding the operation science metrics specifically, we can say that the cycle time stands out as it represents, it's a consequence of what happened with the working process and the throughput metrics that are happening within this production system. And cycle time actually will directly affect project performance in terms of the duration of that specific construction process that we are analyzing. Finally, the conditions in which we develop this case study might open new types of research projects. This was a building project, so we can implement operation science, as we saw throughout the whole conference today, in different types of projects. Another crucial component is that we use prefabricated or pre-assembled EIFS panels. They were developed in a different location and they were only assembled on the construction site. Therefore, this off-site construction component allow us to actually collect more accurate data. If we try to apply this operation science analysis into a different type of project, a more traditional type of a project, we might find different type of difficulties in order to collect data. And that can lead us to develop different types of research projects. I believe that I have some external results, but I can talk about that if we have some more time. I also, before I finish my presentation, I would like to acknowledge the contribution of several people involved in my master's thesis, which is the basis for this research project. I have to mention all of them: Aris Tomaline, Wanda Ryder, Maria Laura Dell, Roberto Bulu, Patricia Tillman, Matthew Wersma, Mike Lesbron, Annabella Pinon, and Chet Carlson. Thank you to all of you for providing your insights and helping me to develop this research project. These are the references shared within the presentation. If you have any more questions after this time that we are going to have, please send me an email.
We got a couple of questions for you here online.
Awesome.
Yeah. Stop sharing your presentation.
Sure.
So we can see you. All right. So what was the reaction of the company you worked with for your study when applying the production system modeling and optimization? Any aha moments for them or for you?
I mean, for me, it was great to see how a model is representing what is actually happening. Having the results of the actual construction process, this on-site assembly of the facade for the building, having this table that compares those two values was, for me, an aha moment that we can actually model construction processes that are traditionally known as very variable. We can use analytical models to represent what's happening. Another aha moment for me was to actually collect data of how we can make these assumptions. And the project team was actually very engaged in lean tools. And when I showed them what the production system did for them, without even knowing that they were doing this production system approach probably. So that was, I believe, an aha moment for them at the same time.
So kind of building on that, has this work influenced your view about the way you look at projects, say, before you got to UC Berkeley and now?
Yes, 100%. I had just a glance of lean and how we can accomplish such improvements with lean when I was in Peru working for public sector institutions. And after coming to Berkeley, I now have a way different perspective how we can implement lean production as a whole, focusing on designing production systems with this amount of metrics and this amount of tools. And what I find most interesting is that we are actually using science to develop these tools, which for construction, and this is an opinion probably, I feel that construction is usually related as an empirical industry. And by using these concepts and operation science in particular, we can actually apply science to what we're doing.
Yeah, empirical meaning seat of the pants. let's see what happens. Yeah,
Yes.
very good. Well, thank you for sharing your research, and I'm sure folks will enjoy reading your paper. And thank you again for preparing it and preparing the presentation.